Okay. All right. So this is the EECE 2310 Exam 1 review for spring 2023. Topics that we're going to be going over, things like logic gates and combinatorial logic, Boolean algebra and using the rules of Boolean algebra to simplify expressions. We'll do some Kmaps, I think. Have you guys talked about Kmaps? Okay. Yeah, Kmaps, some binary arithmetic, and maybe things like muxes, encoders, decoders. We'll see where we get to, but we can jump around too, but there's some basic things that we should probably go over. So first, the logic gates. So a complementary logic, or CMOS, the C stands for complementary, which means that there's a P version and an N version. So the NMOS looks like this, where it has no inversion bubble, and the PMOS does have an inversion bubble. And to remember how these work, I like to think N is for normal and P is for opposite, because when you have an NMOS transistor, an input of the 0 on this input node is basically off, which means that there's an open circuit. There's no conduction happening between the top and the bottom. When you have a 1 on the input, that basically creates a short between the top and the bottom and allows it to conduct. So the PMOS is opposite. It's got this inversion bubble, which says that when the input signal is low, then this PMOS is on and it's conducting. And when the input signal is high, or a logic 1, then it's off and it's like an open circuit or a break. So these are kind of like the foundation of all this digital logic, the fact that we can have an input making an output that's either on or off. Transistors are really just switches at the end of the day, and they switch in this very specific way. So the NMOS, or the normal ones, have this behavior where 0 is off and 1 is on, and then the PMOS is the opposite. So I don't think that you need to do these PMOS or CMOS circuits on your exam, but just in case, and it's good to know. This is a NAND gate, so that's kind of the simplest 2-input gate. So NAND gate, the truth table for NAND is over here. So if your inputs are A and B, and our inputs are 0, 0, then NAND is 1. 0, 1, and NAND is 1. 1 and 0 NAND is 1, and the only time when NAND's output is 0 is when both inputs are 1, because it's the opposite of an AND gate. So an AND gate would be 0, 0, 0, 1. And that one's a little more intuitive because is it true that A and B are both on, or they're both 1, or they're both high? And says, yes, that's true. If either of them are off, or if both of them are off, then AND says that that's false. So that's the AND truth table, and if you just flip every 0 to a 1 and every 1 to a 0, that's the truth table for NAND. And the reason why NAND is so important, NAND and NOR are both basically both really important, is because it's really simple to make it using the CMOS logic. So we have these are PMOS, two PMOS transistors on top, kind of in parallel, and then two NMOS in series on the bottom. And so the reason this works is we have basically these different inputs, A and B. And say, let's look at the case where A and B are 0, 1. Okay, so if A and B are 0, 1, then A is 0. So it helps, and some you might have to do this on your exam, or maybe you don't, but it's good to know anyway. So let's highlight something red if the gate is off and not conducting, and green if it's on and conducting. So if A is 0, we have a 0 coming into this PMOS, and we know from our truth table up here, we would have a 0 on the input of a PMOS. That means it's on and conducting. So this one is conducting, but the B has a 1 on the input of the PMOS, so this is not conducting. So that's like an open circuit. You ignore that. But the green, or the A, is conducting. So we just have VDD conducting down here, acting like a short. So we're shorting V out to VDD. Okay, and so that looks like the output should be 1 right here, right? For the NAND gate. And we know from our truth table it will be, but let's look at the bottom part too. So if A is 0, then we look at this gate. The input is A. We have a 0 as the input to an NMOS transistor. 0 as the input to an NMOS transistor means it's off and it's not conducting. Okay, so that means we can mark this one off here. And B is a 1 on the input to the NMOS gate. So that is conducting. But the A is not conducting. This is like a break in the circuit. There's no conduction happening from ground to V out. So if we were to redraw this circuit with these gates considered and everything, we have our VDD. That's our voltage source. And then this is the NMOS with an A input. That's acting like a short circuit. This PMOS, or the PMOS, sorry, PMOS with A. This PMOS with B as the input is acting like an open circuit. Okay, this is our V out. And then down here we have this A NMOS is acting like an open circuit. And the B NMOS is acting like a short circuit. So we're to look at this diagram with all the transistors opened or shut. We can see that there's a clear conduction path from VDD straight down to V out. These are shorted together, they're the same node. And VDD is our logic 1. So we know our V out has a logic 1. So that's where we get the actual physical behavior of this NAND gate. And you can trace that through for any of these different circuits. Just make sure that you know this truth table. For an NMOS with no inversion bubble, a 0 means it's off and a 1 means it's on. And then for PMOS, it's the opposite. So there's a couple more truth tables that we can do for each of these different logic gates. Have you guys seen all of these logic gates? Yeah, okay, perfect. Let's just fill them in real quick. And I think is easy. Some of them are easy, some of them are a little weirder, but and is pretty easy. Is it true that A and B are both 1? No, it's false, false, false. And only in this case is it true. For NAND, the gate just looks like an AND with an inversion bubble on the outside, on the end of it. So with this inversion bubble, we basically flip all of the logic from the normal case, then the AND case. So 0 becomes 1, 0 becomes 1, 1, 0. And it's basically not AND. Or, I always think it's hard to draw OR gates. It's a little bit easier to draw AND gates, but this is an OR gate. Is it true that A or B, or both, are 1? For the 0, 0 case, it's no, that's a 0. Yes, yes, and yes. Okay, NOR is the opposite again, just like NAND is to AND, NOR is to OR. You can flip all of the logic here, 1, 0, 0, 0. And you can think of NOR as neither A nor B are on. And that's only true in the 0, 0 case. In every other case, at least one of them is on, so NOR is 0. XOR is exclusive OR. That means, is it true that one or the other but not both are on? So for 0, 0, that's not true. Then 0, 1, one is on, but the other is off. That's true. Same for this case. And 1 and 1, this is where it's the not both case. So exclusive OR says no. And XNOR is just the opposite of that one. So 1, 0, 0, 1. And these two are useful later when you get into parity checking on signals. You can basically have a string of bits, and you can have one bit saying, is it an even number of bits or an odd number of bits? And you can use these gates in hardware to check the validity of a message in some rudimentary way. A NOT gate, or inversion, a logical inverter, is pretty simple. It just takes the input. It looks like if it's a 1 on the input, then it's a 0 on the output. And if it's a 0 on the input, then it's a 1 on the output. That's pretty intuitive, I think. Okay, so these are the logic gates. This is pretty much every logic gate you're going to see. Let's get into some Boolean algebra. So these ones are kind of tricky sometimes with all the rule names. And usually you don't have to know all the rule names, but you do have to be able to recognize them. So some really important properties, the identity property. This one I think is pretty intuitive coming from normal algebra. 1 and, remember multiplication is like and pluses are like ors. Okay, so this is like a times or a multiplication, and this is like an or is like a plus. Okay, so the identity property says if you have 1 and something, the result is just that something. So A could be 0 or 1. If A was 1, then we'd have 1 and 1 is 1. So that's the same thing. A was 1, it's 1 here and 1 here. If A was 0, then we would have 1 and 0 equals, 0. 1 and 0 is 0. And so A is still the same in both cases. So we can use 1s and 0s, but if we don't know what it is, we can use a symbol to represent a logic value. And these identities hold for whichever way that symbol is, 0 or 1. Identity in the OR side, just 0 or A is the same thing as A. Basically, ORing a 0 onto something can't change the result. The idempotent property, this is useful for some simplifications. So if you're ANDing two of the same bit together, the result is just a single value of that bit. Basically, 0 and 0 equals 0, and 1 equals 1. That's what that one is saying. In either case, it works out this way. A or A equals A. It's kind of the same thing. A 0 or 0 equals 0, and a 0 and 0 equals 0. So these ones are a little useful when you're simplifying some things. The distributive property, I think one of these is easier than the other to remember. So we've got basically all of these rules work for and for or. They're kind of equivalent operations in the Boolean world, whereas we know multiplication and addition are not the same in regular algebra. So I think the or version is pretty simple. It's kind of the same way that we do it in normal algebra. You can kind of distribute across this or operation. You can distribute the and across the or. So it's A and this sum, and then you can distribute the A and B or A and C. So this property is a little bit easy to remember, but the other one, I feel like people miss it sometimes because these operations really are kind of equivalent. They have the same precedence and everything. So you can do the same thing with this or, and you can distribute it over this and, okay? And it works out to look like this. And the way that I can kind of say that it's a little bit easier to see how these work in either way is that we replace and with a symbol, and then we use parentheses. So in this case, it's the same thing. These two statements are equivalent. But if we write it like this, it's a little bit easier to see that we can distribute this plus sign to both of those. So we can write this as A or B and A or C. Okay, so it really is the same property in either case, but people will miss the this one a lot. So sometimes if you ever get stuck on a derivation, make sure you see if you can distribute an or across two anded terms. Okay. De Morgan's law, this one's really important. I maybe should have left a little bit more space for this one. But De Morgan's law basically says that if you have an inversion happening to a group of terms, you invert each of the individual terms and you invert the operation between them. So and goes to or goes to and. So what's happening here is we have the A is getting inverted, so this inversion is getting distributed to both of these terms A and B. And it's also getting applied to the and that's between them. You can't see it, but there's really an and here. So we get A naught, the and changes to or, and then B changes to B naught. So that's De Morgan's law for and. And it's the same thing in the or world. If we have A or B all inverted, then this becomes A naught, the inversion carries to both of those terms, and it also applies to the operation between them. So this is A naught and B naught, or A naught, B naught. And before I get ahead of myself, A naught and A naught, these are equivalent, just different notation that people use. I think my professor used the apostrophe for inversion, but they're equivalent. And sometimes for parentheses, it's nice to write A, B, all inverted, because you might miss the apostrophe at the end, but they're really equivalent. Absorption. This is another weird one that you don't necessarily have to remember, but it can save you some time if you do. So let's start with the OR version. OR version, let's think of this as factoring. Right? You can think of this one as factoring. So if you had a normal expression like x plus 2x equals something, you can factor out an x and you get x times 1 plus 2. right? You can factor out that x and basically pull it from each of those terms. But you can do kind of the same thing in the Boolean world. So we have A or A and B. We can kind of factor out that A and apply it to the entire term 1 or B. And then usually what we can do in these cases, we can simplify this internal term. So factoring out can help us sometimes. So what's happening here is we have A or A and B. We're factoring out an A from both of these. So we get A and this term 1 or B. And then we remember from one of our earlier properties, 1 or something. Or I guess that we don't have that property, but if you think about the or truth table, if you have 1 or something else, it's always going to be 1. Or is basically asking, is at least one of these 1? And the answer is yes, because we have this guy right there. Yeah. Null element property. Is that what it's called? I think so, yeah. I don't remember the names of all of them, but it's an important one to remember. So when you find yourself in this situation, you can simplify this, right? And the answer is up here. So 1 or B, that's just the same thing as 1. So we have A and 1. Anything and 1 is just itself. So this is equal to A. And that's what we got here. So usually if I saw something like this, I might not remember to just say, oh, this is equal to A. But you can always do these steps to rederive this absorption property. And the same thing works for the AND world. So if you can, if you want to derive this again, right, you can distribute this AND across these two terms. You get A and A or A and B. This one, we know from our idempotent property, anything and itself is just equal to that item. So A and A just equals A, right? And then we have A and B here. And then if we see this A or A and B, that's what we have there. So you can do the same steps to simplify this down to just A, but this is just written in a different form. So sometimes when you're simplifying things using just the Boolean algebra properties, you need to do a little bit of distribution and factoring and reorganizing to make sure that you can simplify it down as nice as you can. And of course, once we get to Kmaps, it's a little bit easier to know when you've done it correctly, but both of these terms simplified onto A. Okay, so let's do an example right here. So it says minimize the following into sum of products form. So I guess maybe I should have gone over the SOP. Well, okay, SOP and POS. Sum of products is when you have different terms and there's the sum symbol or an or between them. This is SOP, right? And then POS is the opposite when you have different terms and they're all multiplied or anded together. This is POS. So these are the two different forms that our answers can be. So let's go back quickly to this example. It says minimize the following in SOP form. So I guess they would usually write that this is an expression with the variables A, B, and C, so that we know how many variables there are. There's 3 variables total. But if we're looking at this expression, the first thing that you might want to do is find terms that have common elements in them. So, for example, these both have an A naught B, and let's go. These ones both have a B naught C. This is A B naught C naught, or sorry, A B naught, right? So if we group them that way, A B naught C naught, or A B naught C, make this a little bit thinner. Or A naught B C or A naught B C naught. Okay, we can kind of do some steps to simplify either one. I'll just move to one color after this. In these two cases, we have an A B naught in both, so we can kind of factor that one out. This is A B naught, and then we have C naught or C. And then on this side, we have an A naught B in both cases. So we can do A naught B and factor that one out. C or C naught. Okay. So this is another property. I guess I don't think I wrote this one down, right? Where you have something ORed with its opposite. I guess we should talk about that property real quick. So in the AND case, gotta take a break from this problem real quick. If you have A and A naught, you know that if one of these is a 1, the other one's going to be a 0. So because this operation is commutative and you can change the order of these around, this is basically saying you have a 0 somewhere and a 1 somewhere. And in whatever case, regardless of what A is, one of them is going to be 1, one of them is going to be 0. It's going to turn out to be 0. For the OR world, if we have A or A naught, same thing. One of them is going to be 0, one of them is going to be 1, and a 0 or 1 is always going to equal 1. So this is another property for simplification that sometimes comes in handy. So in this case, we have C naught or C. So we know from this property that anything or its logical opposite is equal to 1. Okay, so let's kind of skip this section for a bit. Yep. Complement property, yes, that's the name. Did your professor say anything about like when you do these steps, you have to like write the name of the property next to it? Oh, you do? Oh my goodness. Okay. Okay. See, that's a thing because this class has been changing professors the last couple of semesters. So let's call this what was this called? The null element property. Just for posterity. Yeah, make sure you know these properties. Okay, yeah. So if it's important that you know the rules, know the names of these, then make sure you know these. But I would contend that definitely after outside of this class, knowing the names is not as important, but definitely you need to get those points on the test. Okay, so the complement property, right? So we can simplify this down to this is A, B naught, and 1, which again, from our other properties, we could see that that simplifies down to just A, B naught. That is the identity property. So the A, B naught is filling the role of A here. The and 1 is just the identity element, so we get A, B naught here. Okay, and in the other one, we have A naught B. So this is in simplest form. Sometimes people will try and look at it and try and find a way to simplify it because we've got an A in here and we've got an A here, B here, and B here, but we really can't simplify this any further. And when we get to the Kmaps, we know that we could show this visually. Okay. So some distinctions between SOP and POS that sometimes confuses people. So sum of products just means that you have terms with ors between them, and POS means you have terms with ands between them. In the simplest, in the most general sense, the canonical form usually means that all the literals can be found in each term. So that's where we're using our min terms and max terms. So if our function is like a function of A, B, C, the min term might be A, B naught, C naught, A, B, C. You know, a min term has to have all of these. This would not be an example of a min term. Okay, so if something is asked for in canonical form, you probably need to expand it out so that all of your terms or all of your literals are present in every term. So in this case, we just had A, B, and we need to get a C in there. We can use the complement property and the identity property at the same time, and we know that we can AND this with 1. Okay, so this is A, B, and 1. And we know that 1 equals C or C naught. Okay, so we can say this is A, B, and C or C naught. Okay, and then we can use the distributive property of AND over OR to get A, B, C. That's the first distribution. And the second one is A, B, C naught. So if you ever need to expand smaller terms into canonical min terms, this is one way you can do it. And just make sure that you're ending up with the correct form. If we had sum of products here, then we'd use the other complement property rule. We would have like C naught, and then we'd be distributing that across an OR. Yeah. Yeah, exactly. And that's why usually if they're doing something like this, they're asking about canonical forms. They should give you like how many variables there are. If I just told you y equals a b naught, and I asked you, is this in canonical form? You'd have no way of knowing because you don't know if y is a function of just a and b, or if it's a function of a, b, c, d. Without that kind of information, you can't really tell me if this is a minterm or not, or if it has all of the literals in it. So just be careful of that. Usually you're not going to get questions specifically about that. But if they tell you that the expression is a function of 4 variables, then your minterms are all going to have 4 variables in them, like a, b naught, c, d naught, right? And they can be knotted or not, but you just need to have the literal in some form in that term. Okay? Yeah, minterms are product terms. So like these are minterms, and usually when we have a choice, we'll work with minterms. They're a little bit more natural, in my opinion, at least. And I think most people agree with that. Minterms are these product terms in the sum of products form, and max terms are the opposite. So max terms look like A or B naught or C or D. You know, that's a max term because it's OR terms, and then you'd have multiple of these, you know, or so this would be like a product of sums. Each of these is a sum, and the whole thing is a product of these sums. Okay, POS, SOP. Don't mess those up. So min terms versus max terms. So these are, I don't know if you're going to get any like theoretical type questions on the test, but sometimes it's good to know these things just in case. So if you have a function of n variables, there's 2 to the n min terms and 2 to the n max terms. And we usually label these using numbers from 0 to 2 to the n minus 1. So how should I organize this? Okay, so the minterms, yeah, minterms and maxterms start from 0 and go all the way up to 2 to the n minus 1. So if n is 3, 2 to the 3 is 8. So there's 8 total, and they start 0, 1, 2, 3, 4, 5, 6, 7, 8. Not 8, but 0 through 7. There's 8 total. And they're always numbered in this way. And usually we use like a lowercase m for min terms and a capital N for m for max terms. And if you've seen this notation, sometimes the m is omitted here, but this is a sum symbol and this is a product symbol. So this sum symbol is basically saying this is sum of products form. So these are min terms. And this product symbol is saying that this is a product of sums. So these are max terms. Okay? Max terms, min terms. Actually, I write min terms with a lowercase m, so we remember that the lowercase m is min terms. And so if a function has certain min terms, it will not have the same max terms. So the relationship is kind of like this. If we look at all of the possible min terms, if we have a 3-variable function, that is f of a, b, c, right? Let me change my color. It's getting kind of busy with the red. We have a function of a, b, and c. And we know that min term 0 is a naught, b naught, c naught, right? This is min term 0. So we know that this is part of the full canonical SOP form of the expression or of the function. Then we can say that min term 0 is part of that function. Okay, and if we know that 0, 2, 5, and 6 are all min terms that make up that function, then we can write the function in this way. It's the sum of min term 0, min term 2, min term 5, and min term 6. Right, so this would be min term 0. Min term 2 would be, this is M2. And again, the way that you can get these is by thinking in binary, which we'll talk a little bit about binary later, but you've probably had some experience with it. So a binary 2 is a 1, 0. You can always add leading zeros. In minterm world, zeros equate with knots, and ones equate with the non-inverted literals. So minterm 2, this is base 2. This is a 2 in base 10. And minterm 2 is A naught, B, C naught. Okay, it's a 0, 1, 0. Inverted, non-inverted, inverted. Okay, so knowing all of this, if we know that our final expression has minterms 0, 2, 5, and 6 in it, then it has the other max terms. The minterms that aren't included are going to be included as max terms. So if we think about a function of 3 variables has 0, 1, 2, 3, 4, 5, 6, 7, 0, 2, 5, and 6 are in minterms, then the function has 1, 3, 4, and 7 as max terms. Okay, and the same thing is the opposite, the inverse of the function. So if we were to logically invert that function, then the minterms would swap. So instead of having 0, 2, 5, and 6 as minterms, we would have 1, 3, 4, and 7 as max terms. So this is f, and this is f naught, the logical inverse of the function. So this kind of the relationship between the function and its inverse and its minterms and its max terms can save you some time. If, for example, you're given a question and you know that, or maybe you have the equation of the function in sum of products form. So sum of products form means you have all the minterms. If you have all the minterms and the question asks which max terms does it have, or can you write it in product of sum form, then you can look at the minterms, take all the other terms as max terms, and just write the function out using these max terms instead of using minterms. So that's kind of a quick way it can save you some time, and you might get some questions about this. But so I remember that when I took this class, there were a lot of questions about converting between product of sums and sum of products. So there's a couple of different strategies for POS to SOP. So POS would be if you have a product of some terms, so like A, B naught, C. Right? Okay, so maybe say that this is our function. So to get from POS to SOP, usually what I like to do, I think this one is a little more intuitive because you can kind of use the distributive property. And sometimes it takes a lot of time to do it this way, but it's a general strategy. So if we did this one real quick, A, B naught, C, and A naught or B, then we could distribute basically this whole term to each of these. And we could get A naught, A, B naught, C. Or we're distributing this whole term to this B, so we get B, A, B naught, or C. Okay, and then we could do another round of distribution. So we could get A naught A, or A naught B naught, or A naught C. And then now we're distributing this one. A B, B B naught, B C. Okay. In this example, we end up with mostly two literal terms, but this might not be in simplest form. So technically this is sum of products form, but there's definitely some simplification we can do. Like for example, we see we can use the complement property on a couple of these. Let's see. I think those are the only two. A and A naught is always 0. B and B naught, that's always 0. Okay, so we can basically cross these terms out. They're zeros and they're ORed together. ORing a 0 isn't going to change anything. So we have A naught, B naught, A naught C, A B, B C. Okay, so let's see if there's anything else we can do. In a lot of cases, there isn't, and I don't think that there is anything we can do to simplify this. I just made up this example on the spot, so let me think. But yeah, so like if we see that we have an A naught in both of these terms, we could factor out this A naught, and we have B naught or C. but this is no longer in sum of products form. So that's not what we want. So I think this is probably in the simplest form. And we could check with a Kmap later. So maybe we can come back to this. But this is getting from POS to SOP. From SOP, so this is SOP form and back into POS. There's a couple of ways that you can do it. You could do the distribution of the distributive property, the other one that's a little unintuitive. So you could say, I want to get product terms. And so usually what we do is, for distribution, we have something ANDed to a sum, so B, C, and we distribute the AND over this OR operation. Okay? What we can still do is we can do it the other way. If we have B or AC, we can distribute this OR over the AND operation. That's the other distributive property. So what this looks like is, let's switch the color up. We have A naught, B naught. Okay. One way we could do this is do this distribution. So we have this A naught, B naught term. We could distribute it over this AND operation. Okay. So we could say A naught, B naught, A naught. That's the first one. Or A naught, B naught, C. Okay, and of course we can do some simplification here. This is A naught and A naught. That's the, which property is that? The idempotent property, right? So we could simplify this down to just a single A naught, B naught. Okay, and then we get this term, A naught, B naught, C. And we could do the same thing here. Now this strategy gets a little hairy sometimes if you have a lot of terms, because we still have to worry about this A, B, B, C term. And when we do this enough, we might get closer. But there's another strategy that I personally like, and sometimes it's a lot of work, but I like it. So say we have a function. Say we have a function, and we're going from a sum of products to product of sums. Okay. Let's make it a simple function. So this is an f of A, B, C, and we'll call it A naught, sorry, A naught, B naught, C naught. Okay, so this is our function in a sum of products form. So one thing that we can do is we can follow these steps. So apply De Morgan's law to the whole expression to get the inverse of the function. Then we use these steps, the normal distributive property, to expand into a sum of products form. Because every time we apply De Morgan's, it's going to change forms. So we expand it into sum of products again, and then we apply De Morgan's law again to this sum of products form to get f double prime, which is the original function, and then the result is going to be in a product of sum form. So let's see what that looks like. So this is our function. What we can do first is invert it. And we get f naught equals, and we have to invert this whole thing. So we have A naught, B naught, C naught. This term gets knotted. We have to invert this plus to a times. A, B, C naught. This whole term gets knotted. And we have to invert this or to an and then A, B naught, C, this term gets knotted, okay? So now this kind of looks like it's a product of sums, right? And all we have to do is expand this out and we'll get our sums on the inside. So if we do De Morgan's law again for this term, we have this inversion applying to all three of these terms. That gives us an A, B, or C. This one gives us an A naught, B naught, or C. And this final one gives us an A naught or a B or C naught. Okay, so I'm just applying this inversion to all of these terms. Double inversions go back to the original term. So now what we have is f prime or the inversion of the function in a product of sums form. Okay. So now at this point, we can do the distributive property that we did before, and we'll get basically following the steps that we did here. Do this distribution, which is pretty simple and intuitive. It's easy to remember. And we'll get all of these terms, simplify some of them. And then what we do is that's the inverse function. So when we do this distribution, we're not changing the function at all. That's still f naught. It's still the inverse. So if we were to distribute just a couple of these, right? I won't do the whole thing because it's kind of a lot of terms, but you can see kind of the pattern. So let's distribute maybe this first one. This is a naught, a b c, b naught, a b c. Sorry, c, a b c. Okay, so we're just distributing all of these to these three terms, right? The whole first group. So, whoops. Okay. So then if we distribute it again, we'd get more and more terms, but eventually we'd end up with these two literal terms like a naught a, a naught b, a naught c, and everything. And this is still f naught. Okay. And if we were to invert this one more time, then we would get, like we saw here, when we inverted f from a sum of products to a product of sums form. We invert it again. Now it's in sum of products. And we invert it and we'll get a product of sum form. Invert, invert, and this is normal f, and this will be in a sum of products form, or sorry, product of sum form. Okay, I'm going a little bit slow with these examples. I wish we had more time, but I think this is a strategy. It sometimes takes a lot of steps, but it will get you there 100% of the time. And if you're not allowed to use Kmaps to do it, and you're not allowed to use the min terms and the max terms, then this is a surefire way using the principles of Boolean algebra. These properties that you have to know, like De Morgan's property. So this is just one way to do it, and there's probably cleverer ways to do it. If you have fewer terms, if you have more terms, it might be more efficient to do it just kind of by doing distribution or by factoring out. But this method works in a vacuum, regardless of what the expression that you're given is. Okay, so let's move on. It's a lot of Boolean algebra that we've been doing. Let's do some Kmaps because Kmaps are really useful. And we can come back if we have time. But okay, Kmaps. So Kmaps are sometimes squares and sometimes they are kind of rectangles. If you have a function of 4 variables, this would be like f of a, b, c, d, and you'd have 2 variables going down this side and 2 variables going down that side. And this would be if you have a function of 3 variables, then we could do like 0, 1, 0, 0, 0, 1, 1, 0, sorry, 1, 1, and 0. So remember, the sides are numbered with gray code, and gray code is a sequence of bits that from one to the next only changes 1 bit. So usually when we count in binary, we go 0, 0, 0, 1, 1, 0, 1, 1. But if you look from the second to the third term, both bits are changing. This one's changing from 0 to 1, and this one's changing from a 1 to a 0. And it's not super important, I think, that you know why that's necessary for Kmaps, but basically what Kmaps allow us to do is group neighboring patterns together. And these neighboring patterns are differing only by 1 bit. And that lets us kind of ignore the other bits and only focus on the ones that are changing. And that helps us simplify our expressions. So you probably don't need to know any gray code past like the 2-bit versions. But there's a method for generating gray code where you basically copy the list in the reverse order. So 0, 0, 0, 1, 1, 1, 1, 0, that's for 2 bits. You copy it in reverse order, so you go 1, 1, 0, 1, 1, 0, 1, 0, 0. And then to the first set, you add a 0 out front. And to the second set, you add a 1 out front. And that doubles the length of your gray code. So if you need to do it for more and more variables, you can always build it out that way. But usually you can just remember it if it's just for 2 bits here. Okay? So for drawing a Kmap, if it's a 4-variable expression, then we have 2 bits going down either side. 0, 0, 0, 1, 1, 1, 1, 0. And for a 3-variable Kmap, you can have one side that just has 1 variable, switching between 0 and 1. And the other one has 2 variables on it. So this could be like A, B, C. Okay. Then for minimizing Kmaps. So minimizing Kmaps is, a lot of people struggle with it when you first start, but once you kind of get it, you get it. So the rules are, and you probably have at least developed some kind of intuition for these, maybe, is you always draw the biggest circles, starting with, for a 2x2, you'll start with circles of size 4. So either circles that contain 4 elements like this, or circles that contain 2 and 2 like that. You want to start with the size 4, because you can't get much bigger than that. Then you do the size 2 ones. So like anything that's size 2. And if there's still a term that you can't get with any size 2 or size 4 bubbles, then you can circle it by itself. Okay? And we'll do some examples in a second. You want to draw the fewest circles as possible. So if you have any overlap, like for example, so we have a couple of 1s here, you could draw 2 double circles, but you can get it with just 1 big 4 circle. Okay? This 1 circle will suffice. Similarly, if we had a pattern like this, we could draw a 4 circle like this and a 4 circle like this. Or we could draw 1 big circle containing all of them. So you want to draw the biggest circles as possible, and usually that'll lead to you drawing the fewest circles possible. Got to make sure that every single one of your 1s is covered if you're doing midterms. And then you have to go find out what group is represented by that circle and write it out as an equation. Okay? So let's do an example. Okay, so this is writing a function given a Kmap. So the first step is drawing the circles, and then the second step is identifying what the equation is from the circles. So let's say we have an equation of A, B, C, and D. And so let's draw our circles. Well, we can see we're going to start with like the big size 4 circles. We can draw one right here. We can draw another one with these 4 ones. Okay, and there's only 2 ones that aren't covered. And remember that we can draw circles that kind of wrap around the edges. So this is a size 2 circle. This is a size 2 circle that's containing both of those ones. So this set of circles covers all of the ones that we have, right? So next is we need to figure out what the equation should be from these circles, and we're going to write a minimized equation. So let's start with this tall circle, I guess an oval. So we see that the K-map is labeled like this. The left side represents A and B, and the right side represents C and D. So what this column is saying is that for all of these cases, C equals 1 and D equals 1. Okay? So each spot on the K-map is going to represent some minterm. And the minterm that it represents is specified by all 4 of the bits. So for example, if we look at the minterm represented by this corner, we have A, B, C, and D in that order. In this corner, A and B are 1, 0. So A, B, C, D. Let's just write this below it. A and B are 1, 0. And C and D are also 1, 0. So this is minterm number, well, if you convert this to binary, or if you convert this binary number into decimal, you get the number of the minterm it is. It's 2 plus, not 4, but 8. It's 10. Okay, this is minterm number 10. But what's really important is to know how do we write that in our equation. So this minterm would be A, B naught, C, D naught. Because wherever we have a D is 0, that's D naught. B is 0, that's B naught. Whereas the A, which is the first number, and the C, which is the third number, those ones are not inverted, so they stay as A and C. Okay, so that's kind of the general way that we get a minterm from a 1 or a 0 on here. So what we're concerned with is the ones that are inside the circle. So if this tall circle is representing the case where C is 1 and D is 1, but between all the cases of this circle, A and B are changing, then we can say that it doesn't matter what A and B are. Every case where C is 1 and D is 1 is going to be represented in this circle. So this circle is just CD. And so you can remember that if you have 4 terms in your Kmap, circle of size 4 has 2 terms, or 2 literals. As the circle sizes get smaller, if it's a size 2, that's 3 literals. And if it's a size 1, it'll have 4 literals in it. Okay, so the biggest circles have the fewest number of literals. So this tall circle represents CD. This wide circle here, if we look at what this one represents, I think these ones are a little bit trickier because this one, CD is 1, 1. We can always remember that because it's just this entire column. But this wide circle kind of flips between 2 of them. So we need to look for what terms are staying the same in all spots in this circle. So if we look at our A is 1, regardless of which box we're in. They all fall under this case where A is 1. Okay? So we can write down that A is 1. A is going to have no inversion. And B is changing. So B is going to be omitted from this term because it's changing between boxes that are within this circle. Okay? B is changing, so we don't add that. We don't write a B down. What else is staying the same? This first number represents C. C is going from 0 to 1 in between boxes that are represented in this circle, so we don't write C down. But D in both of these columns is 1, so we'll write that D is 1. All right, so this is another 4-element circle that's represented by 2 literals. Finally, we have this smaller circle, this 2-element circle. Okay, this 2-element circle, where we need to look at what's staying the same and what's changing. So in this row, both of these terms are in this row. So that means A and B, they're both 0, 0. That's true for both of these boxes. A is 0 and B is 0. We're talking about this row. Okay? So we can write down immediately that A naught and B naught are part of that literal. They're part of that term. And then the other thing that stays the same is D is 0, where C is changing. So we can write D naught. Okay, so this is the equation that we get with all of these ones covered. That's the process for determining how you get from Kmap to equation. And you can do plenty of examples like this, but if you understand how to kind of figure out which term is represented by each circle, then you can help check yourself to not make mistakes. Okay, we can do another Kmap example, or we can move on. Did you guys do like binary arithmetic and adding and stuff on this exam? Okay, let's move on to that then. We can come back to Kmaps a little bit later. Maybe we can do one with max terms as well. So binary as a number format. It's a little funky when you first do it, but once you understand it a little bit, it's just a couple of steps that you need to follow. Okay, so binary is base 2, meaning that you have only 2 symbols that can represent numbers, zeros and ones. In base 10, we have 0 through 9. That's 10 total symbols. That's base 10. And in base 2, we only have 2 symbols, zeros and ones. And the bits all have different representations. So the first bit of a number, so if our number was 1, 0, 0, 1, 0, 1, 1, 0, we can look at a table like this. The first 0 represents the 2 to the power 0 case, which is a 1. So this is saying, do we or do we not have a 1 as part of this number? If the number here is a 0, that means it's 0 times 2 to the power 0. That's 0 times 1, which is 0. Okay, if we have a 1 here in this second position, this is saying we have 1 times 2 to the power 1, which is 1 times 2, which is 2. And when we do this for all of these steps, we add the results, and we get our number in base 10. Or decimal, as it's called. Okay, so this number, for example, would have 1 times 2 to the power 2, 0 times 2 to the power 3, 1 times 2 to the power 4, 0 times 2 to the 5, 0 times 2 to the 6, and 1 times 2 to the 7. And you might, as you go, start memorizing the powers of 2 up until maybe like 10 or 11 or 12. But you can usually just derive them again if you know 2 to the 1 is 2, double it, double it, double it, double it. That's pretty easy to do on pencil and paper. Okay, so this number would be 2 to the 7 is 128, so this is 128, plus this is 0, this is 0, 2 to the 4 is 16, so this is plus 16. This one is 0, 0 times 2 to the power 3, that's 0. 2 to the power 2, that's 4, plus 2. Okay, so this would come out to be 16 plus 4 is 20, plus 2 is 22. 128 plus 22 is 150. If my math is correct, 150 in base 10, right? So this is the number in base 2, and this is the number in base 10. They're the same number, just written using different representations. Okay? So for adding and subtracting, you can, well, okay, this is like the different methods for converting a decimal number into binary. So you can, this is like the adding method, kind of the guessing and checking. One of the other ways that you can do it is, say we have the number 75, okay? And we divide by 2. Okay, 75 divided by 2 is, maybe we should just do this like this. 75 divided by 2 is, this is a 3, and then this would be a 7, and we have a remainder of 1. Okay? So then next what we do is 37 divided by 2. And we're noting the remainders off to the side here. 37 divided by 2, this is a 1. And then this would be a 8, right? With a remainder of 1. 18 divided by 2 is 9, with a remainder of 0. 9 divided by 2 is 4, with a remainder 1. Run out of space here. 4 divided by 2 is 2, with a remainder 0. And then 2 divided by 2 is 1, with a remainder 0. And then finally, 1 divided by 2 is 0, with a remainder 1. So this method, you keep taking the previous answer and you divide it by 2 again, all the way until your answer is 0. And then when we look at the remainders in reverse order, we get our number is 1, 0, 0, 1, 0, 1, 1. Okay? And this should, with any luck, be 75 in base 2. Okay, so this is the division approach. This one's a little, you don't need to know your powers of 2 outright for it, but it doesn't lead to as much insight, I think, as the adding and subtracting way. So they're both ways that you can convert between a number in base 2 and base 10. If you're given a binary number, of course, you can just add up the powers of 2. So look at it, make yourself a table like this, and kind of go in the reverse way and say, if I have a 1 here, let's 2 to the 7, so like this. And if you're given a number in binary or in decimal, you need to convert it to binary. You can either kind of say, okay, 75, that's probably 64, that's a power of 2, plus, if we subtract out 64 from that, we're left with 15. 15 we could break down into 8 plus 4 plus 2 plus 1. Okay, so you could do it in that way too, where you just kind of note the powers of 2 and write them out. So that's converting between base 2 and base 10 is really important. We can do more examples of that too. Did you guys talk about rounding binary fractions? Okay, because this is something that it was never covered in this class until like I think a couple of years ago they started doing it, but it was just the other professor I think that did it. So I don't think this is going to be on your exam. How about 2's complement? Do you guys do 2's complement? Yes, okay. 2's complement. So 2's complement is how we can represent negative binary numbers. The idea is basically in the decimal system, in the normal base 10 system, we have 4. -4 is the number such that 4 plus -4 equals 0. Okay, and it's really easy for us because all we got to do is tack a negative sign out front. In binary, if our number is 1, 0, and we want to add to it something that gives us a result of 0, 0, how do we do that? Well, we can't really subtract something. We're only adding here, because subtraction is really just adding a negative. So we need to add something that gets us a 0 and a 0 on the output, right? That's really the idea of an additive inverse or a negative. So let's try a 0 here, and let's put a 1 here maybe. So if we did this, we'd get 0, we would get 0 carry the 1, and we would get 1. Okay? So this gets us 0, 0, but we have an extra 1 out front. Well, when we're doing negative numbers in binary, we kind of have to deal with the fact that we're going to have overflow. That's the only way that we can make the numbering system work. So this is fine to have this 0, 0 with a 1 extra out front, because usually in these systems we're using computers, we only have so many bits. This extra 1 is just going to disappear. It won't affect any of the hardware of the system. Or we can log it and say, okay, there was an overflow on this operation. But the idea behind it is that we need some kind of number that when we add it to the original number, we get 0, 0. So, yes. Usually you do. It depends, because when you have a final carry at the end, that's indicative of some property of your number. So we'll talk about in a second. But yeah, so 2's complement, the method for finding your number in the negative version of your number. So say we had the number 7. 7 is 1, 1, 1 in binary. And we can always have zeros out front of a number. So if we want to get a -7, this is our 7. If we want to get our -7, we have to flip all of the bits. So this would be 1, 1, 1, 0, 0, 0. And then we add 1 to the smallest bit. So we get 1, 1, 1, 0, 0, 1. Okay? So this looks like a much bigger number because we have all these 1s out front. But just like how for a positive number, you can always add zeros out to the left, for a negative number, you can add as many 1s out to the left as you'd like. Up until the minimum number of 1s that you need is 1 of them to specify this as a number, a negative number. So usually what you need to do is you need to have an extra bit to represent your number. So the reason we do this is because, okay, let's just start here. So this is a -7. Okay, and we can double check that this is 7 plus a -7, which is 1, 0, 0, 1. This should result in us having zeros at the bottom here. Let's check. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And 1 plus 1 is 0, and we'll carry a 1. Okay, so we do end up with an overflow bit here. Yes? Good question. So the reason I added the 0 here is because it's let's talk about what kind of numbers we can represent. Say our system only has 3 bits to work with. Okay, we only have 3 bits to work with. Then normally we can represent any number from 0, 0, 0 to 1, 1, 1, which is 0 to 7. Or 0 to 2 to the n minus 1. Okay, that's the general formula. If you have n bits, you have 2 to the n minus 1 is your largest number. Okay, so say that we were using 3 bits and we wanted to represent the number 7. That's 1, 1, 1. Or let's say 6. We've been using 7 a lot. 1, 1, 0. Okay, if we want to represent the number 6. Now, if we want to represent the number -6 using 3 bits, then let's do our process. This is 6 To represent -6, we flip all the bits, so that becomes 0, 0, 1. And we add 1, right? We add 1. This becomes 0, 1, 0. Okay, so that's our -6. This is our -6. The problem is that this is also 2. 0, 1, 0, that's 2. That's a binary 2. So if we're working with 3 bits and you had 0, 1, 0, that's 0 times 2 to the 0, 0 or 1 times 2 to the 1, and 0 times 2 to the 2. That's a 2. Okay? So when you expand your numbering system to allow negative numbers, you have to sacrifice some of your range to do it. So we can't actually represent. The reason this is a problem is because when we're dealing with this number, we don't know if this 2 is this is a 2 or a -6, right? So if we imagine that we have a range of numbers, and let's call this is 0, okay? And this goes all the way to 2 to the n minus 1. This is our range of numbers of width n in a positive only world, okay? We have this many numbers. If we want to use negative numbers using the same number of n bits, then we don't get any more numbers to work with. We just have to shift our range down. This is still, oh, sorry, this is like 2 to the n number of numbers. So let's say that this is 0, 1, 2, 3, 4, 5, 6, 7. Okay, with 3 bits, we can represent all of those numbers. With 3 bits in 2's complement, we can't represent all of those numbers and their negatives. We just don't have that kind of resolution to be specific, because when we tried to represent a -6, it was also a 2, right? So what we have to do is we kind of have to sacrifice some of our range. So we can no longer represent numbers up to 7. What we can do is we can say 0, 1, 2, 3, -1, -2, -3, negative. Okay, so if we count how many numbers this is 1, 2, 3, 4, 5, 6, 7, 8. And we count up here 1, 2, 3, 4, 5, 6, 7, 8. So we could represent the same number of numbers using the same number of bits. But the range of the numbers is slightly different when we use 2's complement. Okay, and this is just because you can't create information out of nothing. If you have 3 bits and you can only represent these digits, this number of different options, you can't create more possibilities by including the negative numbers. You have to sacrifice some of your positive numbers. So back to the question of why did I write a 0 in front of my 7? Because to represent a -7, we need to have 4 bits. Okay, and that's a really tricky concept to get down. But it kind of is like a natural extension of the numbering system. When you include the negative numbers, you need more bits to represent those numbers. So that's why I added a 0 here, because I knew that when we got a -7, we would need to have a 1 here. We would need to have 4 bits to represent that this is a negative number, not just a 1. Yep. Yeah, so if we looked at what we could represent with 4 bits, so up here I said that with 3 bits, you can represent numbers from 0 to 2 to the n minus 1. And this is unsigned. Okay, this is unsigned, only positive numbers. With signed numbers, hey, let me write this a little cleaner. With signed numbers, with the 2's complement system, you can represent numbers from negative, oh, scary, -2 to the n minus 1 to 2 to the n minus 1 minus 1. Okay, and this is kind of a wacky formula, but this is really just representing us shifting our range downward so that we can represent as many numbers as we want. So say that we want to represent a -7. A -7. Well, -7 is close to -8. where -8 is -2 to the power 3. Okay, that's -8. So your exponent here is 3. -2 to the n minus 1. That's 3 is our n minus 1, so our n has to equal 4 in order to represent a -7. I know that's not the best way of explaining it, but yeah, you need more bits to represent certain things. And for this class, you probably don't need to remember all of the ranges, but like 2 to 3 to 4 bits, you can remember that with 3 bits, you can represent these numbers in the positive domain. Or if you're using 2's complement, you can go -4 up to +3. And that's just the way that it works. There's this, I would pull it up. There's this other representation using a kind of a circle that I always found was really confusing, but I think some people it works for. But there's plenty of resources online to kind of visualize 2's complement and to see why it works this way. But let's keep going. Did I miss anything? Okay, yeah, so the overflow bit. So there's another question about the overflow bit. So there might be overflow. If we're using a 2's complement numbering system and we're adding, say we have 4 bits, and we're adding 2 plus 2. This is 1, 0 plus 1, 0. Well, let's do that addition. We have 4 bits to work with, remember? 0 plus 0 is 0. 1 plus 1 is 0 carry the 1. So we're left with 1, 0, 0. This is a binary 4. There's no overflow that happens here. Okay? So there's not always going to be overflow when we're working with a 2's complement numbering system. But when we are, there's some cases where overflow can happen. If you're adding a positive number and you're subtracting a number, so you're moving closer to 0. If you have a positive number and you're subtracting a number, you're not going to get overflow. Same with if you have a negative number and you're adding a positive number, you're not going to get overflow. But it's only when you're approaching the edges of this regime. So say that you're doing 2 plus a positive number, you might wrap over to the other side. That's overflow. Okay, so if we did 2 plus 2 in a 3-bit 2's complement numbering system, 2 plus 2 would try to give us a positive 4, but we can't represent a positive 4. So that would overflow back to the other side. Okay, so if we tried that, we tried 2 plus 2 in 3-bit 2's complement. Okay, we tried to do 2 plus 2. 2 is 1, 0. Or 0, 1, 0. The other 2 is 0, 1, 0. But we need to flip this to be a negative. Okay, so -2 would be 1, 0, 1 plus 1, which is 1, 1, 0. Okay, that's a -2. So here I flipped the bits. 0, 1, 0 becomes 1, 0, 1. And then I added the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. And 1 plus 0 is 1. Okay, so we have our 2 numbers. We have our 0, 1, 0. That's our 2. And our -2 is 1, 1, 0. Oh, yeah, you're right. We did 2 plus 2. Okay, my mistake. Yes, we're doing 2 plus 2. 2 plus 2. Okay, 2 plus 2. 0, 1, 0. Okay, yeah, this is actually a really good question because this is going to sound kind of unintuitive. Okay, 0 plus 0 is 0. 1 plus 1 is 0, carry the 1. And 1 plus 0 plus 0 is 1. Okay, so this looks like a 4, right? This looks like a binary 4. This is 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0. Okay, but let's try to use this 4. So we can make it negative. So this is a, let's call this a 4 question mark. If we try to make it negative, then we flip the bits. 0, 1, 1. Okay, we flipped our bits, and then we add 1. What do we get? 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. So this is our -4. But you see that it's the same thing, 1, 0, 0, 1, 0, 0. That's a 4 and a -4. So if we're using this system where we only have 3 bits to work with, how are we going to know if we encounter this number, if it's a +4 or a -4? Well, what we do is we define it as a -4. Okay, so that's kind of the tricky hand-wavy things that we have to do with the two's complement numbering system. It's really tricky to kind of understand it, but the reason why, or like the one intuition is for why we call this a -4 and not a +4, is because when we look at our numbers, let's see, we have 0, 0, 0. Okay, and then so these are all of the different combinations of numbers using 3 bits, right? It's pretty natural for us to say, well, these ones have a 1 as the first bit, and these ones have a 0 as the first bit. Let's call these the positives and these the negatives. Okay, if we do that, then this is our 0, 1, 2, 3. These ones stay the same, right? That's just normal binary. For the negatives, it's a little weird. Why is 1, 0, 0 a -4? Why is this or this is our -1 technically? What we end up doing is, if you imagine the number line, here's the number line. Okay, we have our 0, 1, 2, 3. So our 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. What we do when we reach the positive maximum is we wrap around the bottom side, and that's an overflow, and this happens in computer science as well. If you increment an integer past however many bits it has, it goes to the negative integer maximum. So then we call this -4, -3, -2, -1. And if we look at what the binary representation of these numbers is, without doing the bit flip and add 1, we just keep counting. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so let's double check some of these. Let's try to do 3 plus -3, and we should end up with 0. Okay, so 3 is 0, 1, 1. -3 is 1, 0, 1. Is 3, -3. Okay, we get 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. Okay, we're still only concerned about these 3 bits. So we do get a 1 here. This is our overflow. Okay, but these 3 bits are zeros. Okay, so that's what matters. We're only concerned about those 3 bits. So that's kind of the intuition behind two's complement. And working with it is the same as working with normal binary numbers. You just have to remember that however many bits your system is, however many bits you're working with, anything past that is just an overflow. Okay, so that's probably, does this make a little bit more sense? Okay, let's trying to think if there's anything more that we missed. I mean, of course, there's going to be like arithmetic problems where maybe your teacher will say, like, give me like 4 minus 3 and do the operation in binary. Well, then you're going to have to work out how many bits you need. In this case, you would need 4 bits, right? And then you'd have to find 4, you'd have to find -3 and perform the addition. But the nice thing is, you know, the answer should end up being 1, however you get there. Okay. Have you guys talked about binary coded decimal? Okay, because I don't remember covering this when I took the class, but I remember last semester some students told me that their professor covered it. So okay, well that's good news. And okay, if you do need to know this, uh, there's a process for it. It's basically if we had like 47 plus 6, then we perform the binary arithmetic using each digit separately. So we'd convert this to 4, which is 1, 0, 0, 1, 1, 1, 1, 1, 0. And then we can kind of do this addition. Okay, perfect. I'll skip it for now. Yeah, I don't think it'll be in this class then. Usually if it's anywhere in this class, it's on exam 1. Muxes, decoders, and encoders, right? That's on this exam, right? Okay. Muxes. So muxes are really nice because they allow for some really cool things to happen in computers. You have kind of like a railroad track, you have multiple tracks coming in, and then you can switch it that one track comes on the output. Okay? And it's controlled, of course, like everything in a computer, with binary. So the notation that we use for mux is like a 2 to the n power, 2 to the k power to 1 mux. So an example, it'd be if we had 4 inputs, there's always going to be 1 output. And what the mux is doing is basically selecting which of the inputs to tie directly to the output. So this would be like a 4 to 1 mux if we have 4 inputs and 1 output. And the number of inputs is always going to be some power of 2. So that's why we can write it as like 2 to the k. Okay? And with the mux, we're selecting one of these input lines to be tied directly to the output line. So we need to be able to address each of these lines. We need to be able to have a specific combination of bits that can uniquely represent one of these 4 lines. So if we number them 0, 1, 2, 3. We think about the numbers 0, 1, 2, and 3. We need 2 bits to represent these 4 numbers. We can have 0, 0, 0, 1, 1, 0, and 1, 1. In that way, with 2 select bits, we can pick those select bits to be one of these 3 numbers. So if our select bits are 0, 1, that's a binary 1, which means that we're going to pass the data line number 1 to the output. Okay, so the number of select bits that you need is related to the number of inputs you need, and it's related using this expression. So if we have n inputs, then we'll have log base 2 of n select lines. Or to say that in the other way, if you have little n select lines, then you can have up to 2 to the n data lines. And that goes back to just binary numbers. If you have n bits, you can represent 2 to the n different numbers. So if we have 2 to the n different numbers that we can represent, then we can specify which one of them we want uniquely. So the mux, I think, is pretty straightforward. It's a little tricky to just kind of get this whole idea of addressing down, but you can make a truth table for it. So if we called this input 0, input 1, input 2, input 3, never forget to start counting at 0. Once you start dealing with computers more, you're going to start counting at 0. So say that our select lines are K1 and K0. That's these 2 bits. This is K1, K0. By setting those bits, this is a binary 0, this is a 1, this is a 2, this is a 3. We can directly select which of the inputs we want to pass through to the output. So if the select lines are 1 and 0, that means that's a binary 2, so we're going to put input number 2 through to the output. Okay. And later on, you'll use these. You can do truth tables using muxes by hard coding the inputs and using the select lines to pass through an output. But that's for 3320. Okay, so that's muxes. Decoders. Actually, let's do encoders first. So encoders, they encode a signal or a series of inputs into a binary output. Maybe I should do decoders first. It doesn't really matter, but if for an encoder, you'll have 2 to the k inputs the same way, and you'll have k outputs. So you could have 2 inputs and 1 output. we could have 4 inputs and 2 outputs, but it's still going to represent that, it's still going to follow that same relationship where the number of outputs you have, the number of inputs you have, this will be k, and this will be 2 to the power k. So your inputs can always be up to a power of 2. Okay, so what the encoder does, and it's easy to get them mixed up, the encoder and the decoder, but the encoder, I like to think that it encodes something into binary. So you take some set of inputs, and out you're going to get a binary number. So usually what it'll do is it'll take a 1 hot input, or it'll have a priority system. Which means if we label these as 0, 1, 2, 3, 4, 5, 6, 7, so that's 8 inputs from 0 to 7. Say this is the highest priority. Have you guys covered priority encoders? Or did you mention that? Okay. So okay, so hopefully there's not a lot of questions on the exam, but basically what you would expect is you have an input where all of these are zeros and maybe one of them is a 1. And what this does is it takes whichever one is a 1, this is input number 4, the output will be a binary 4. So let's say that this is y0, y1, and y2. We have 3 output bits. If input number 4 is high, then our outputs y2, y1, and y0 are going to be 1, 0, 0, because that's a 4 in binary. Now, what encoders don't handle well is if your input is all zeros. So that's one thing to note about encoders. Note. If the inputs are all zeros, that's considered invalid. And the reason is, say we were coming up with some system to, we're going to be mapping these inputs. We're basically detecting which of these is high. I think, I'm trying to remember what the physical example that we did, but maybe like you have a bunch of like pressure plate sensors and you're trying to detect which of those sensors went off. So if you have all the signals coming in, like this is sensor number 0, sensor number 1, sensor number 2, and you want to get the number of the sensor on the output, what's going to happen is, let's say sensor number 0 was going off. Okay, these would all be zeros, and sensor number 0 would have a 1. So what you will want your system to do is output 0, 0, 0 to say this sensor number 0 is going off. Okay, so the output 0 of all zeros is associated with a 1 on input number 0 and zeros everywhere else. Now, if we had an input of all zeros, what would that output mean? It means that none of the sensors are going off, but we don't really have a binary number for none. We have 0, but 0 refers to this sensor. So for an encoder, usually if you have all zeros, that's considered an invalid input. So in a perfect world, your encoder is going to have one of these is 1, and the other ones are going to be 0. In some systems, that's not possible. So they'll have some workaround for it, like a priority system, but that's probably not going to be on this exam. Yeah. So that's where like the priority thing goes on. So like in some systems, say you had the 6 was 1 and the 0 was 1. In a priority encoder, this would output 110 for 6, because the 6 has the higher priority. So that's something like maybe you have like a bunch of different devices hooked up to a computer, and they're all signaling like, hey, I need you to send me some data. You can have the highest priority. So that's why a priority system works really well for an encoder, because the output is going to be referring back to a single line. So like the output is going to say 6 needs your attention. If 0 also needs your attention, then you have to come up with some system, because usually you need a one hot input, meaning that only one of them is high. Okay. But yeah, that's probably not going to be on, if you haven't talked about the priority system yet, then that's probably not going to be on your exam. Decoders are the opposite, and they work a little bit nicer because there's no invalid inputs. There's no worry about priority systems. Decoders take a binary number and they decode it back into a one-hot output. So again, we can label our outputs as 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7. Okay. And our input is going to be a binary number. And our output is going to be one hot. I guess I didn't define that. One hot means that you have all zeros and one of them is 1. Exactly one of them is 1. Okay? It means like one of the elements is high and the other ones are low. That's what one hot means. So the binary decoder will take in a signal. Let's say the signal is, and it's important when you're doing these types of things to know what order the bits are going. So if I told you 0, 1, 1, you need to know which of these is the least significant bit and which of them is the most significant bit. So let's say that this is our input 0, input 1, and input 2. So E0 is the least significant bit. So we'd write our number like I2, I1, I0, like 1, 1, 0. That's our input. Okay, and what the decoder is going to do is going to say, okay, this is a binary. Let's figure out what this is. 0 times 2 to the 0, 1 times 2 to the 1, and 1 times 2 to the 2. This is 2 squared plus 2 plus 0. That's 4 plus 2 equals 6. So some of these numbers you're going to get more familiar with reading the binary numbers more quickly, but you can always do this process. So this is a binary 6. So it's going to turn output number 6 to 1, and all the other ones are going to be zeros. Okay? So this is really useful actually for like memory addressing. So say that you had in your computer, you have like a list of memory locations, you know, like all these zeros and ones stored on your hard drive. And this is memory address 0, 1, 2, 3, 4, and whatnot. And say I wanted to access memory address number 3. I could pass a binary 3, which is 0, 1, 1, into this decoder. And what the decoder would do, it would give me a 0 for all of these, and it would have a 1 on output number 3. And that could be saying like, if there's a 1 here, then that means read that data. So the decoder is pretty useful for like reading and writing and addressing into memory banks and everything. But for the decoder, remember you're taking a binary input and you're decoding it out into a one-hot output, where the 1 exists at the number specified by the binary input. So if the input is a binary 6, then output number 6 is going to be high. If the input is all zeros, then your output is going to have a 1 at output number 0 and zeros elsewhere. Okay, so that's the decoder. Muxes, encoders, decoders. I would hope that you don't need to know like all the internals of these things. Do you think you need to know those? Probably not. Yeah, I think no, yeah, usually that kind of thing is kind of like the theoretical derivation type thing, and you don't have to remember how to do that. So I wouldn't worry about that too much. Oh, okay, yeah, sure. So you can have an enable signal. And what that means is, so say you have a system like a memory bank, and if nothing is using the memory, then the inputs might be 0, 0, 0, right? So say this is your memory decoder. If there's no signals on anything, like these might be zeros or something, just from they're zeros. You don't want this thing to be constantly trying to read memory location 0. Right? So if there's 0, 1, 2, 3, 4. So that's the motivation behind an enable is saying there's always going to be some input here, which means that there's always going to be one of these is a 1 somewhere. And we don't want to be messing with things when we don't want to mess with them. So With the decoder, we might have an enable signal, which means that if the enable is a 0, then all of your outputs are going to be 0, regardless of what the input is. Enable being 0 means that this device is off. It's not doing any calculation. It's not doing any thinking. Whatever the input is, we don't care. All of our outputs are zeros. When the enable is 1, that means we do want to decode the input and pass it through to the output. So if all the inputs are zeros and the enable is 1, then we'll send a 1 out to the output and we'll read that memory allocation or whatever we need to do. But yeah, the enable is important. And so in your logic, whatever logic that is, it's kind of like, say that this is some kind of logic. The enable is basically ANDed, and the enable signal. So if the enable is 0, then all of this logic turns to 0 because we're ANDing a 0. And if the enable is 1, then it's some logic and 1, which just passes through whatever logic you have. So the enable kind of just kills any thinking that's going on inside of the decoder and sets all of the outputs to 0. And otherwise, you have this one hot output, which is, there's kind of some duality between the encoder and the decoder. For the encoder, you don't like to see an input of all zeros because then your output doesn't know what to do. And for a decoder, you're not going to see an output of all zeros unless you have this enable pin, unless you have an enable set to 0. If your enable is high, then you should never have an output of all zeros because whatever binary number this is, it's going to have a 1 on that output number. Okay, so we covered a lot of things. Is there anything that we missed? Anything that you talked about in class that we didn't get through today? At least even a little bit? Okay. So what's nice about these reviews is the last couple of years we started recording them. So you can go back and look on the IEEE YouTube channel and find older reviews. And I think I did maybe the last 1 or 2 of them, so they might have mostly the same content, but you can look back and I think a couple of years they might have different examples, different professors. Some of the things might not be the same, but if you want different explanations of concepts, you can look at those videos. But other than that, yeah, you can always message on IEEE Tutoring Discord if you have any questions about specific topics. Most people in EEC have taken this class, and so they'll understand how to do things like binary arithmetic. And we didn't get a lot of time spent on binary arithmetic. Oh, did you guys do binary multiplication in this chapter? Okay, yeah, I think that's usually like an exam 2 thing. Okay,
addition and subtraction and just a bunch of conversions.
Yeah, okay, that sounds about right. Making sure you know how to convert between base 2 and base 10 is really important, because when you start dealing with like computer systems and logic and everything, like everything's stored in binary. So if you want to be able to understand what's going on, you need to be able to convert it. Usually the computer will do it for you, but sometimes you need to be smarter than the computer. Kmaps, we didn't get an example of the max term. So for Kmaps, if you're dealing with max terms, right, you'll want to look at the zeros. So we're going to we draw circles around where the zeros are. So for this case, we might draw a circle here. Sorry, circle here to get these zeros. And then maybe we'll draw another circle here, these zeros, and then another one here. Okay, so this is just an example of using max terms. And the reason I think max terms are a little more confusing is because the zeros and the ones are kind of swapped from what makes sense. So for example, if we look real quick at just this bubble, in this bubble, let's see. In both of these rows, A equals 1, and B is changing. So we ignore B. And in both of these columns, let's see, in both of these columns, our D is 0 and our C is changing. So D equals 0. Okay, so we have a bubble where the things that's constant in this bubble, in this bottom 4-piece circle, A is 1, D equals 0, and we're dealing with max terms. A equals 1 means A naught, and D equals 0 means D. Okay, so this would be our sum term to make a product of sum expansion of this equation. Oh yeah, sorry, I should have done these in different colors. This is this circle here. So when we're doing max terms, we can circle the zeros, and this helps us get a minimized form for the max terms. And for min terms, we circle the ones, and we get the min terms. And of course, you can always do this in the other way. Like if you get an equation like this, you can do it minterm style, get your minterms, and then invert your minterms. So for example, so there's one little bit on the Kmap section that I didn't quite get to. It's counting your minterms and your max terms. So if you have a Kmap, each one of these blocks basically represents a minterm or a max term. And they go in order of gray code. So this is like M0, the 0000 case, which means A naught, B naught, C naught, D naught. This is minterm 0, right? Or A, B, C, D is lowercase m0. This is max term 0, okay? When all of them are 0, that's the zeroth minterm or max term. And in your Kmap, you're either going to have a 0 or a 1 here. So let's just say in this case it's a 0. That means that max term number 0 is present, and min term number 0 is not, because min terms you're looking for the ones. So let's just say these are not binary numbers, but in this case it is. This is min term number 1. That represents 0, 0, 0, 1, 0, 0, 0, 1. That's A naught, B naught, C naught, D. This is min term number 0. Write that M a little smaller. Min term 0. And because there's a 1 there, then if we were writing out all of our min terms and max terms, we would write that this is the sum of the min terms 1, yada, yada, yada. And max term 0 would not be there. So did you guys talk about this notation in your class? Yeah, okay. So say that we had this expression and we had min terms 1, 2, 3, and 6. Then we would know by default that we have max terms 0, 1, 2, 3, 4, 5, 6, 7. And I won't go all the way up to, because technically for 4 bits you have up until from 0 to 15, but that's the idea. Basically, the sets of your min terms and your max terms are going to be, I think disjoint is the word. Disjoint is the mathematical term for they don't share any common elements. And one final thing before we close out, because I always get a little long-winded with these explanations of Boolean algebra, but when you're counting your minterms, make sure you don't forget the gray code. So this is kind of counting in order for the minterms. So like, we count M0, M1, M2, M3, M4. If you're looking at a Kmap and you're trying to figure out which minterms I have, this is M0. This is M1. And then we skip, this is M2, and then this is M3. Okay, that's because of your gray code. And you can always go back and look at the binary numbers, like this square right here, 0, 0, 1, 1. That's 2 plus 1 equals 3. Okay, even though it's 0, 1, 2 is the second, it's like kind of element number 2 if we were counting 0, 1, 2. Because we're using gray code, you have to be really careful when you do that. 0, 1, 2, 3, 4, 5, 6, 7. And then it even works down the other side. From 7, here we go 8, 9, 10, 11, and then 12, 13, 14, 15. So minterm number 15 is actually located in this box. So just don't get mixed up on that, because that happens all the time. Like if you're given a question like this, find the minterms of the function, you might be tempted to go, okay, we've got 0, 1, 2. Oh, sorry. 0, not 1, but 2 and 3. In this case, it works out for you. But then if you go, okay, not 4, not 5, we have minterm number 6, and not minterm number 7. Well, this is not minterm number 6. This is minterm number 7. So just be careful of that. Same with max terms. You're counting your zeros as 0, 1, 2, 3, but they're max terms. And you're counting zeros for max terms. Okay. But yeah, I think that's mostly everything. I don't think the binary fraction rounding is going to be on if you haven't talked about that, which is nice because that's very confusing sometimes. Anything else? Any other questions? All right. I'll go ahead and end the recording. This will be posted on YouTube shortly. But otherwise, good luck on your exams.